on this computer. Okay, so we're recording finally. And I hope you guys can still see this whole screen as the shared screen, is that right?
No, I don't see the shared screen anymore. I don't know if the other people can or not, but.
All right, hold on. Let me hit shared screen again. What about now? Is it working now?
Yeah, it's fine.
It works now?
Yeah.
Okay. All right, so once again, a group is a set of elements that has these four properties. And the reason why we study group theory in physics is that physical transformations naturally form groups. And the way this is the case is, suppose you have some physical transformations that act on some objects and they leave some property of the objects unchanged. So some property unchanged. It can be very simple, such as just interchanging the order of the objects. And so it obviously, it leaves the objects unchanged, the set of objects unchanged, but only changes their order. Something is ringing in my ear. There's a phone call. I just can't take this phone call. Okay, sorry about that. Jeanette, could you call Rachel and tell her I couldn't speak with her because I'm teaching, please? So for example, if you have a physical transformations acting on some objects and the transformations leave some property of the objects invariant or unchanged, then these transformations always form a group. And I gave the trivial example of a permutation group where you just change the, you imagine the order, the objects in a line, you line them up and then you change the order of the objects. That's the basis of the group of permutations. Another example is points in a plane, and you might move the points in the plane, but in such a way that the distance from the objects from the center of the plane remains invariant. And that's how you get the group of rotations. And the reason why transformations form a group is, of course, if one transformation leaves the property of the objects unchanged, and if all the transformations leave the property, the chosen property is some special property, the objects unchanged, then the product of any two, one transformation followed by a second transformation, will still leave the property unchanged. And moreover, if you can always invert the change. If you do one transformation, you just can do the inverse transformation. So that's the inverse. The identity is just to do nothing. And associativity is a natural consequence of transformations acting on groups of objects. So transformations naturally form groups, and that's why they're important in physics. So as I said, the permutation of an ordered set of n objects changes the order but leaves the set unchanged. Groups of, let me make this scale bigger. I don't see why it has to be so small. The set of transformations that leave invariant the distance from the origin of every point in n-dimensional space, that's the group ON of rotations and reflections. The rotations by themselves in n space form what's called the special orthogonal group, it's called SON. linear transformations that are just displacements for different vectors A leave invariant the spatial difference x minus y between every pair of points in n-dimensional space. This is the group of translations. And here group multiplication is actually vector addition. So you can have x prime equal x plus a, you can have x prime equal x plus b. In fact, I should go back to this. To go back to this. So in other words, you can say x prime is equal to x plus a, or you can say x double prime is x prime plus b. And so that's equal to x plus a plus b. So here you have addition plays the role of multiplication, of group multiplication. And then you can have vectors x0, or, well, I could just say t or ct, x, y, z, and have a matrix such that we have over here ct prime, x prime, y prime, z prime. And this will, so this is a 4x4 real matrix here. And if x squared plus y squared plus z squared, the primed ones minus c squared t prime squared is equal to x squared plus y squared plus z squared minus c squared t squared, then this is the Lorentz group of Lorentz transformations. On the other hand, one can say, well, what we want here is not so much to leave, not just to leave this, but we can also say we want just to have, so we can say that we want, well, let me just use the screen here. x1 minus y1 squared, x2 minus y2 squared, x3 minus y3 squared, minus x0 minus x0 squared, minus y0 squared. To keep this constant for any two 4 vectors, this is the Poincare group. So this is Lorentz transformations plus translations. Now, if you have a translations, then you can translate this way, and you can translate that way, or you could translate this way first and then translate that way, and you get to the same point. So we say here that the order doesn't matter. T prime is equal to T prime T for translations. And groups that have this property, which we would say is that the transformations commute, the order doesn't matter, where this by definition is T prime minus T prime T. If this is equal to 0, then we say the group is abelian. And that's named after Niels Abel, who unfortunately had a very short life. I guess Norway was a somewhat more exciting place than one normally would imagine. So if you have a set of square matrices, if the determinant, so you have a bunch of matrices D, and if the determinant of all of these matrices are non-zero, then and if they're square, then you have inverses, such that that is the n by n identity. Matrix multiplication is automatically associative. If you have A, B, C is automatically A, B, C for matrix multiplication. So you automatically have all the properties. The only one that's tricky is that you want to have that if two matrices, D1 and D2, that this is some matrix D3 that still leaves unchanged whatever the property is of the vectors that you're talking about. When you're talking about when the elements of the group are square matrices, then they would, if they're n by n square matrices, then they act on n-dimensional vectors. And so there's some property of n-dimensional vectors that these matrices leave invariant. And what prevents any group of any set of non-singular matrices from being a group is that the only thing essentially that can break down, well, one thing that can break down is this. Of course, they always have an inverse, but the inverse may not be in the set. Well, if we say the inverse is in the set, then the key property here is what's called closure. In other words, so that you get closure basically if and only if all of the matrices leave some property of the vectors unchanged. I don't know if I've never heard of that being a theorem, but I think it probably is. So another example is the orthogonal groups. These are real matrices that leave unchanged the square distance of a point from the origin. The group O2n leaves unchanged the anti-commutation relations of the real and imaginary parts of n complex fermionic operators. So that's one application of the group O2n. The n by n orthogonal matrices of unit determinant, they form the special orthogonal group SON. Special, denoted, written capital S, means simply that the matrices have unit determinant. The reason why that is important is that transformations that leave the squared distance invariant could include the reflections, and we want to just if we want to narrow down to the group of rotations, then we impose the requirement that the determinant of the transformation be +1. Unitary groups come up a lot in physics, especially quantum mechanics. And the set of all n by n complex matrices that leave this quadratic form invariant is the unitary group UN of n by n unitary matrices. And these of unit determinant form what's called the special unitary group. So remember, a unitary, first of all, what is a unitary matrix? Written by a dagger. This is the transpose of the matrix times the complex conjugate, or the transpose of the complex conjugate. So actually the sensible way is to write it as U complex conjugate transpose. And it's unitary if U dagger U is equal to U dagger is equal to the identity element, the identity matrix. And it turns out that SU2 represents rotations. And so it's, in fact, this is rotations for fermions, or at least for spin 1/2 fermions. in the past 40 or 50 years, well, maybe not quite that long, the groups SU5 and SO10 have been used to unify the electroweak and strong interactions. This is called grand unification. Whether it actually is true in nature is still unclear. The set of all 2n by 2n real matrices that leave invariant the commutation relations of quantum mechanics of n variables. In other words, leave invariant these commutation relations is the symplectic group. By that, what I'm talking about is that Qi prime would be Rij Qj, and or rather that, all right, the Qi's would be that, but then P K say prime would be R K P L K L, and you see the problem is here that what we would have is a vector Q1 up to, let us say, Qn, and then P1 up to Pn, and then we'd have this matrix R, and this would be Q prime 1, Q prime n, P prime 1, P prime n. So that's what I meant by what I was trying to write this way. I don't know. And, I'm often going to be summing over repeated indices. And so Einstein introduced the convention that AI, BI is the sum of AI, BI. And he was talking normally about spaces, space-time 0 to 3. People really don't like to have to write this sum sign over and over and over again. And so what has become a kind of convention in physics is to say that that dot products of any kind, Q dot P, which is, say, a sum I equals 1 to n of Qi Pi, well, we're just going to write it as Qi Pi. And because you have the same index here as here, that implies that we have a sum. So that's, this is called the summation convention. And it just saves time, but it's more than saving time. When you look at formulas like this, your brain has to process this symbol, and that distracts you from the fact that you're just summing over these guys. And so the simpler the notation, the easier it is to understand what's written in the physics, as long as it's not, completely obscure. Now, the number of elements in a group is the order of the group. And if there are only a finite number of elements in the group, it's said to be a group of finite order or a finite group. And the principal examples of that at least come to my mind are the parity group, whose elements are 1 and -1, and you just have ordinary multiplication, and this is called the cyclic group C2. So the whole group is 1 times 1 is 1, 1 times -1 is -1, -1 times 1 is -1, and -1 times minus 1 is 1. And you can see 1 inverse is 1, minus 1 inverse is minus 1. And so that's the whole group Z2. This group obviously is abelian and it's of order 2. A slightly more complicated version is if you go in the complex plane and pick these points here and here and here and so forth around, and these points are e to the I 2 pi k over n, and you take k goes from 1 to n. When k is n, you just get 1, and so that's a point right here. And then the others are distributed around the unit circle. So these are the elements of the cyclic group Zn, which is of order n. It's abelian. And another group of infinite order is simply the integers. And the integers, just n1 plus n2. That's, in other words, their multiplication is, in other words, abstract multiplication is just defined to be addition. And then you can see that all the normal rules apply. N1 inverse is minus N1, and multiplication is associative. The identity element E is just the integer 0. Let's see, does anybody have a question?
Evan, I have a question.
Yeah.
You'll take questions from non-students.
Yeah.
In the symplectic groups, you said that you implied, or maybe said that the Q's just transform into other Q's and the P's just transform into other P's. There's no mixing of coordinates and momenta. Is that correct? Did I understand that correctly?
That's the way I was thinking of it. Now, that's a good question, though, whether, yeah, I think one probably has to do that, but I would have to think about it, but I think that's right.
That there might be like hybrid coordinate momenta.
Right, but the
variables.
You see, since the Q's commute among themselves and the P's commute among themselves, I think it's dangerous to mix them. But I mean, I could be wrong. It could be possible. In fact,
isn't that what
one student project that we could launch right away is just take the case of n equals 2, and so then you'd have 4 by 4 matrices, and so what are the matrices that would leave invariant? Just the commutation relations for Q1, Q2, P1, and P2. And, you know, in other words, think about that particular case and answer the question that was just posed to me. I think you shouldn't mix the Q's with the P's, but I could be wrong. And then as a more interesting project, can you define a group that does mix the Q's and P's? And if so, what is it that what property of the Q's and P's would they leave invariant? But whether that makes sense as a project, I don't know. It's just something that I'm saying off the top of my head. But that was a very good question, and I promise to think about it tonight, or after class, let's say. Of course, also, if any of you is curious, you could pop ahead to the part of my book where I actually discuss the symplectic group, And you might get an idea of how to answer that question from that section on the symplectic groups. But I think right now I should just continue with the more elementary aspects of the lecture, which is what I actually intended to talk about. Symplectic groups are they're actually underused in physics, even though, as I said, there are these examples, which is to say that leave invariant the commutation relations. Despite that, they're hardly ever mentioned in physics classes, and I've long suspected that at some point people will start using the symplectic groups for something in physics. All right. Anyway, let's go on now to continuous groups. A group whose elements depend continuously upon a set of parameters is called a continuous group, and it's also called a Lie group in honor of Sophus Lie, who first talked about such groups. Continuous groups are of infinite order because obviously if you have continuous variables, then you immediately have infinitely many points. A group of matrices is compact if the squared norm of the trace, that is to say the trace of d dagger d, is bounded for all elements or all matrices in the group. Then we say the group of matrices is compact. And that's true for these classical groups, the special orthogonal groups, the special unitary groups, and the unitary groups. These are all continuous groups of infinite order, and they're all compact because d dagger d is the trace of the identity. In the case of the orthogonal groups, you don't need the complex conjugation because the orthogonal matrices are real, and maybe I should have said that. O star equals O for the orthogonal groups. I think, I hope I said that. Let me just make sure I said that. Yeah, real matrices, so you don't need complex conjugation. So there are also non-compact groups, and in particular, the Lorentz group is non-compact. The set of all real n by n matrices is non-compact. That's called the general linear group. And if you have, you impose that the determinant is unity, then it's SLNR, that's the special linear group. And if you allow the matrices to be complex, then it's GLNC. And if you say the determinant's 1, then it's SLNC. And these groups and the symplectic groups have matrix elements that are unbounded. They're non-compact. They're continuous Lie groups of infinite order, like the orthogonal and unitary groups. And curiously, SL2C represents Lorentz transformations. In fact, that's how Lorentz transformations of two-component spinors transform. And in fact, there are two ways in which you can represent the Lorentz group by SL2C. And those two different ways are why Dirac Spinners are four-dimensional, because what you have when you have a Dirac spinner, you have a left-handed spinner of two components and a right-handed spinner of two components. And under a Lorentz transformation, psi prime is one of the, so this is D left and D right acting on psi left, psi right. And so this is a four-dimensional, this is 4 by 4. Oh, I'm sorry, there is a big 0 there and I left out, this is 0. and this is 4 by 4, and this is 4-dimensional. And so a Dirac spinner is composed of a left-handed part and a right-handed part, a left-handed two-spinner, right-handed two-spinner, and they transform according to two different representations of the Lorentz group by the group SL2C, and they're simply related to each other. It's one can use complex conjugation or to relate them, possibly another minus sign. There are various ways in which one can do that. This is covered, by the way, in, hold on, let me, here in the Lorentz group, left-handed and right-handed representations. And but let's stay with the elementary stuff for the moment. And there's also something known as a semigroup. That's when you have multiplication that's closed and associative, but you may lack an identity element, and you may lack inverses. And the integers form a semigroup, with multiplication being the usual multiplication. So you have associativity, you have closure, because the product of any two integers is an integer, but the inverse of an integer is a fraction. You do have an identity element, that's just the number 1. So that's a simple semigroup example. Now, one of the things that is an important concept in physics is the representations of groups. Mathematicians like to talk about abstract groups, but physicists like to compute things, and to compute things you typically need matrices or vectors or functions or numbers, at least. And so the idea is that some square matrices, one for each element of a group, is a representation of the group if their multiplication imitates that of the group. In other words, if FG is FG, which it must be, then the matrix that represents F, D of F, the matrix that represents G, D of G, has to, the product of those two has to be the matrix D of FG, which represents the matrix, the group element FG. And that has to be true for all elements in the group. If the matrices are n by n, then n is the dimension of the group, of the representation. This is also the dimension of the vector space on which the matrices act. And the representation is unitary if the matrices D of G are unitary. And so what in quantum mechanics, one often deals with unitary representations of groups. And in first year quantum mechanics, or let's say in both graduate and undergraduate quantum mechanics, a lot of attention is paid to the group of rotations in three-dimensional space and the representations of the group of representations, the group of rotations in three-dimensional space. And if we're just talking about rotations in three-dimensional space, then the you remember you have states LM, where M goes from minus L plus 1, ... up to L minus 1L. So that's 2L plus 1 different vectors for each L, L being orbital angular momentum, M being the Z component. And those are the states then that are used in quantum mechanics to represent a ordinary rotations. Now, so in particular, there are defining representations of SU2 and SO3 are just complex matrices. In the case of SU2, they're these matrices. And in the case of SO3, these are real matrices where C is cosine, S is sine. I've written them out explicitly, no reason for you guys to puzzle over these in great, don't worry about them. It just happens to be. In fact, an easier way of writing this thing is to say that d of theta is equal to e to the I theta over 2, a theta vector dot the sigma Pauli matrices, and right. And this actually represents an inverse matrix, but I don't know. Maybe I should have put in. I would have if I were. The actual rotation is e to the minus I over 2 theta dot sigma. But that would have meant I had to put extra, would have had to put extra minus I. Anyway, compact groups possess finite dimensional unitary representations. And of course, by unitary, I mean, I'm including orthogonal representations. So in other words, if the matrix is unitary and real, then it's orthogonal. So compact groups possess finite dimensional unitary representations, but non-compact ones don't. And a group of bounded matrices is compact. And we saw that in the case of what we said was that the trace of d dagger d was less than some number m, then these matrices then are they have bounded they're bounded matrices, and they form if they form a group, they form a compact group. An abstract group is compact if the space of its parameters is closed and bounded, and these are terms that either one learns or one doesn't in a math class. The idea is that in n-dimensional space is the set of all points that are inside but not on the boundary of a circle of a sphere of radius r. This is then an open set. If you include the boundary, then it's a closed set. And more generally, a set is open. We can call this a neighborhood. A neighborhood is some sphere of arbitrary size in the space that includes the point, and that's a neighborhood of the point. And a set is open if each of the elements lies in a neighborhood that lies in the set. So if you have an open set, then if you have a point here, you can find a little sphere around it that's still in the set. Whereas if you have a closed set, you include the boundary, then you got this boundary here. And if you want to include the boundary, then you've got points outside. If you try to include the boundary in an open set, a neighborhood, you've got points that are outside the set. Anyway, the group of rotations is compact, but the group of translations and the Lorentz group those are non-compact. Now, a concept that's simpler and more important than compact and non-compact is the idea that if you have one representation of a group, you almost always can find another representation of the group. And the reason the reason why that is true is that If, in other words, D of G times D of F is D of GF, then it's also true that S D of G, S inverse, S D of F, S inverse is equal to S D of GF, S inverse. And that's because these two guys, this is just equal to the identity element. And this is called a similarity transformation. In other words, an n by n matrix that has a non-zero determinant maps any representation into an equivalent representation in this way. Well, I did it on the notepad the opposite way, but anyway, it's S inverse ds or SD S inverse. And the reason is simply this, which is what I wrote down. So in other words, there are infinitely many, if you have any representation of any group, there are infinitely many equivalent representations. And that is both an advantage and a disadvantage. I think it's, well, it's the way it is. And it's, I guess, mainly an advantage. Another concept that's less important but worth mentioning is a proper subspace of a vector space. This is a subspace of lower but not zero dimension. And so, for example, suppose we're in three-dimensional space, which we might write as R3, then we've got vectors that are in a plane. And so we might have the unit vector in the x direction looking like this. The unit vector in the y direction might look like that. So the plane, the set of all points in this plane is a proper subspace of three-dimensional space. And to get to the rest of the three-dimensional space, you add a vector in the z direction. And a proper subspace is invariant under the action of a representation if the matrices map every vector in the proper invariant subspace if they leave it in the proper invariant subspace. So in other words, rotations about the z-axis like this will leave the plane as a proper invariant subspace. That will leave the plane invariant. And so now we can imagine about a representation of the three-dimensional vectors. If that representation leaves the plane invariant, then we would say it would be a reducible representation. And then, of course, a representation that's not reducible, we say is irreducible. In any event, a representation is completely reducible if you can write it in block diagonal form like that. And in fact, that's what we typically do one way or another in quantum mechanics, is we really like to have representations that are completely reducible. And one might, for example, consider rotations, and one might be doing rotations on on an atom, say, or on simply an electron about moving about a charge of infinite mass, then we might have just the number 1 for the S state, and then for a P state, then we would have a 3 by 3 matrix, and then for a D state, a state of L equals 2, this would be a 5 by 5 matrix. This would be L equals 1, this would be 3 by 3, and this would be L equals 0, which is just 1 by 1, and this would all be zeros. And so we would say this would be a completely reducible representation of the rotation group on this quantum system. And obviously it's inefficient to consider matrices that look like this, because we could just focus on D1 by itself and D2 by itself, and that would be a simpler problem. Or we could analyze the most general D and be done with it for all of the elements on the diagonal, all the different representations. In any case, if the matrix is then some, let's see, I might as well get the same order here. All right, D1, D2, D3 with zeros here. Then we would say D is equal to D1, direct sum D2, direct sum D3. And that would be then a sum of 3 irreducible representations. Here I'm assuming that these 3 guys are irreducible, which is often written as just IRR. Well, the next topic is, although let's see if there's a question from someone, a student or non-student. A question would be, questions are
I have a question, Kevin.
yeah.
And you can't even throw me any candy, which is really the sad part. But so rotations in 3 dimensions, that's not reducible to 2-dimensional rotations plus, right? You can't, the general 3-dimensional rotation, even though 2 dimensions is a, what do you call it, subspace.
Right, the 2-dimensional, in 3 space, the 2-dimensional plane is a subspace of the 3-dimensional space, and you could have transformations that leave the plane invariant. And
well, the general rotation in 3 dimensions is a 3 by 3 matrix, or represented by 3.
Yeah, absolutely. And
that cannot, that's irreducible.
Well, I mean, it depends on which one it is, right? But the whole group of 3 by 3 matrices is irreducible.
Right. If you took a subset of those matrices that describe rotation about the z-axis, of course,
that would be right.
Golden.
Right. That thing would look like this. It would have some complicated structure there.
And then a 1.
Have a 1 there.
Thank you.
Right. Oh, you're welcome. So, of course, in quantum mechanics, what we're interested in is rotations that, or we're interested in transformations that act on states. And we say we have a symmetry if the probabilities are invariant. So a symmetry transformation G is a map from psi to psi prime that preserves probabilities. So we get the inner product of phi prime with psi prime squared, absolute value squared, is equal to the absolute value squared, the inner product of phi with psi. And of course, what I forgot to do here, I should have said phi goes to phi prime and psi goes to psi prime. That's really what I should have said there in this sentence. In ordinary quantum mechanics, what we focus on is operators that are linear and unitary. And there's another kind that's allowed, at least in principle, and that's linear operators that are not linear, that are antilinear and anti-unitary. And these make a lot of use of complex conjugation. And these are back here in equations 195 and 196 of chapter 1. So if you flip back there, you can see that. We're not going to, well, maybe I should go back there and just say what they look like. So if you have an antilinear transformation on these states, you get a complex conjugation here and then K acting on the state. And anti-unitary means that K on the state, the inner product of K on one state and K on the other state is the complex conjugate of the inner product of phi with psi. And so there's just a lot of complex conjugation going on when you have anti-unitary operators. And this is, as far as I know, let me say, I have not seen anti-unitary, antilinear operators used for anything except time reversal. Now, it may be that other people have made use of them more generally, but I've not seen it. So it's a very special thing as far as I know. Anyway, this proof that any symmetry transformation is represented either by linear and unitary or antilinear and anti-unitary, that was first done by Wigner and extended somewhat by Weinberg. Two operators that commute are said to be compatible in quantum mechanics, and a set of compatible operators is said to be complete if to every set of eigenvalues, there's only a single eigenvector. So in other words, you could use these physical operators to distinguish any two physical systems. So, so in other words, you might have a beam of electrons and they're all moving in the same direction at the same speed. What is it that how can you tell them apart? Well, by their spin or the z component of the angular momentum. And that was something that was first exhibited, of course, by Stern and Gerlach a long time ago. And in fact, when they first exhibited it, it was the first sign of spin 1/2 and caused quite a commotion in physics. So let's maybe do an example of rotation operators, because they're what's important, very important in quantum mechanics and in quantum field theory. So suppose you have a Hamiltonian and the square of the angular momentum and the z component of the angular momentum, suppose they form a complete set of compatible observables. So that means A, they commute with each other. And of course, JZ is part of it's one component of a 3 vector, but J squared and H are scalars, and if the Hamiltonian's invariant under rotations, then JZ commutes with H, and J squared typically would commute with H. And so here and in fact, I could have used L squared and LZ here. Probably should have actually. So then you can write the identity operator as a sum of outer products over the energy eigenstates, the angular momentum eigenstates, and the Z component of the angular momentum eigenstates. So the idea here is that this state H on the state EJM is some energy eigenvalue E of EJM. J squared on EJM is equal to J plus 1 and H bar squared EJM, and JZ on EJM is equal to M H bar EJM. And these operators all commute with each other. And so these are the sum of outer products. By the way, one of the things that Dirac invented notationally was this this symbol here for the what he called the bra. This is the ket, that's the bra. The matrix element of a unitary operator between two states, then, since these form a complete set of states, you can stick in two identity operators, one here and one there. So what's done there is just to write phi is phi I U of G, I psi, and then the I's are the sums of outer products here and there. And so one just does the sum. Now, if we assume that this U is representing a symmetry transformation of the Hamiltonian, such as a rotation, then U dagger HU is H and U dagger J squared U is J squared. Well, that tells us that this is true and that's true. And so since we have these relations, which are the ones I just wrote down here, what we can do is we can say HU on the state is UH on the state, and that's EU on the state. J squared U is UJ squared. J squared gives us the JJ plus, I've set H bar equal to 1 here. So what that means then is that U does not change the energy or the angular momentum. And so what we've got is that the matrix elements of U are diagonal apart from the M part. And these then form, actually they typically form a representation of the rotation group. And then it's a matrix that is 2J plus 1 by 2J plus 1 square matrix. And it's associated with the quantum number J, which is the same, has to be the same in both sides here. And so that matrix element, which is a double sum, is actually just a single, I wrote this as a, right, it's a single sum, instead of being a sum over 6 variables, it's a sum over 4 variables. And so we have EJM psi, phi EJM prime, and then this quantity here. And so this then looks like this is then a block diagonal form that appears automatically, and this is how it appears automatically. And the matrix DJ then turns out to be unitary because the operator U is unitary. So let's see, as always happens when students don't ask a lot of questions, I ramble on too quickly, and I feel as though I've covered too much material for an introductory lecture. So the one purpose served by questions is to slow me down to a more appropriate rate or pace. On the other hand, of course, the main purpose of a question is to elicit an answer to the question.
Maybe I'll jump in here and I'll ask a little question that I was just
Yeah.
thinking about. So can you go back to that example where we were talking about like two-dimensional rotate, this subgroup of rotations in the plane of the full three-dimensional rotation group?
Right, okay,
So-
so we've got a plane here, and
Mhm.
there's the y-axis, and then there's the x-axis, and this is the z-axis.
Yeah, yeah, and so we were talking about how certainly the full three-dimensional representation of the rotation group is irreducible. Right, you can't diagonalize all those matrices simultaneously.
Right. Yeah, that's a.
However, if we restrict it to a subgroup, just this subgroup of rotations in the plane.
Right. Those are which are equivalently rotations around the z-axis.
Yes.
Or it is more general than that, because you could rotate about another axis in the z direction, but one about the point, for example, 1, 1. And
sure.
And that would be a different transformation in the plane. Although, to tell you the truth, those 3x3 rotation matrices, normally we're always talking about rotations about the origin. That's what we normally, when we speak of a rotation, we speak of the rotation about the origin. And if we instead rotate about this, then we're picking this as the origin rather than this point here.
We sort of need to talk
But anyway,
fine translations.
Your question. What was your question?
Yeah. Oh, yeah. So the question was that so there we immediately get that there's this invariant subspace, which is just this one-dimensional subspace along the z-axis, right? All right. However, there's kind of an observation that all of these matrices now break down into just one of these standard 2x2 rotation matrices, and just a 1, right, in this like bottom right-hand corner.
Yeah.
Cool. However, those 2x2 rotation matrices, those can be diagonalized, right? Like certainly that the group of just rotations in the plane is totally abelian. And so certainly like I can diagonalize all of those matrices. Well, and their eigenvalues are like e to the I theta.
This thing is equal to cosine sine minus sine cosine, right?
Yeah. So I can diagonalize it if I allow the.
Well, you can certainly diagonalize it, but
you need complex numbers, right?
You have to diagonalize it differently for every angle.
No. They're all simultaneously diagonalizable, right? Every single one of them has a unit vector has an eigenvector which is 1 and I over square root 2 and 1 and minus I over square root 2. Right, those are.
I see. You're going to a complex representation there.
Yeah. So I guess this is herein lies my question, is like, whenever we were talking about the rotation group, we were only ever really talking about real valued vectors, right? But then once I start to ask about, well, can I reduce this representation? I mean, it seems like we sort of need to expand our language to now be talking about complex valued vectors. I mean, I don't know. Yeah,
right.
Should I talk about two different notions of reducibility of a representation, or should I just always consider?
Well, you see, you've got to say what it is that we're talking about. You see, these things here that we were talking about were 3 by 3 real matrices. And so what you're at, or this part here was a 2 by 2 real matrix. But what you point out is that rotations in 2 space can be represented simply by complex numbers, e to the I theta.
Yeah.
Cos theta plus I sine theta. And so that's certainly true. But then what you've done is you're no longer talking about a 2 by 2 real matrix. You're talking about a 1 by 1 complex matrix. And
so would we say that the group SO2 has a real 2-dimensional irreducible representations, but all of its complex irreducible representations are 1-dimensional? Would you say something along the lines of this?
I think I would say that, yes. And that's an interesting point. And of course, when you go to spin 1/2, you bring in complex numbers automatically, because the group is SU2, whereas this one here was SO3 or SON in higher dimensions. And this is SU2, so the thing is, it's e to the I theta dot Pauli matrices divided by 2. And so here you're talking about 2 by 2 complex matrices.
Sure.
So maybe I'll mention something about subgroups. If all of the elements of a group also are elements of another group, then S is said to be a subgroup of G. So in other words, what you've got, so for example, we could talk about rotations about the z-axis. These are all, these form a group, and these all are elements of the group of rotations in 3 space, rotations about the origin. And so we would say then that the rotations about the z-axis are, or about any particular axis, are a subgroup of the whole group of rotations. And one obvious observation is that every group has 2 trivial subgroups. One is the identity element itself. That forms the identity element itself forms a group, and the whole group forms a group. And the group formed by the identity is a subgroup of the whole group, and the whole group is a subgroup of the whole group, because we didn't say it was that S couldn't be the whole group. And so what we talk about is, I think we use the term proper subgroup. So the example is the one we've been talking about over and over again. So a subgroup now of a S of a group G is an invariant subgroup if every element of the subgroup is left inside the subgroup under the action of every element of the group itself, the whole group. So in other words, G inverse SG is S prime. If S is in big S, then S prime is in big S. And so then we say that S is an invariant subgroup. And a nice way of writing that is G inverse S, the whole subgroup G is S for all G in G. And so sometimes it's written this way. And invariant subgroups are also called normal subgroups. And so this is an important concept and a very basic one, and it's easy to understand. Just one more example is the rotations are a subgroup of the group of Lorentz transformations. And the Lorentz transformations are a subgroup of the group of Poincare transformations. So those are three examples, or two or three examples from among the examples that we've been talking about earlier today. So maybe I should say, since we're basically out of time, let me just sort of say what I would think about talking about. These are some mathematical aspects of group theory that we should go through at some rate. But then I would focus upon continuous groups, and it turns out, obviously, if you have a group that's an n by n matrix, so it's an n by n matrix that depends upon continuous parameters, these alphas, that's obviously something quite complicated. Well, it turns out that you can, let's just call that D of alpha. If instead you can define things that are called the generators, which would be the derivative or the partial derivative of D of alpha with respect to, say, alpha I, a particular alpha, and we'd call that T sub I, and we take this derivative where all the alphas are zero. Then these guys, these TIs are the generators, and they, it turns out, form what's called a Lie algebra. And this is then, in other words, under commutator multiplication, they're closed. And this forms then an algebra. Well, the Lie algebra is vastly simpler than the continuous group. So the algebra is just vastly simpler than the group, than the continuous group, let us say. And so that's the subject of Lie algebras here. And then, of course, the one application of continuous groups in quantum mechanics and quantum field theory is Yang-Mills theory. And then other things to talk about are, well, symplectic groups in more detail, and all of the compact simple groups. We've actually already mentioned almost all of them, but there are 4 or 5 special cases, the special classical groups. And then, of course, we'd like to focus on the Lorentz group and the various representations of the Lorentz group, and how they relate to Dirac's representation and so forth. So those would be the things that I propose to do. Now, we don't need to do all of these things in complete detail. In fact, it would be useful if someone would send me an email saying what it is that you'd really like to focus on. Or for that matter, would you rather skip lightly through group theory and concentrate instead on general relativity or probability or Monte Carlo methods or path integrals or one of these other topics? And So let me know. And the other thing is that we need at least, I think, 3 students to register for the course. Otherwise, it will just cancel. The department will cancel the course. So maybe you can, you have some friends who might want to take group theory and, or I mean, take this course 467. Another thing I've thought of is it would be possible perhaps for me to split the course into one course on one subject, such as group theory or general relativity or probability or path integrals, and another 1-hour seminar. In other words, split a 3-credit course into 3 1-credit courses, each on a different topic. And because some of you may be interested in relativity and not care about groups, and others may be interested in path integrals and not care about groups, and so forth. But what we need are people to register for the course. Otherwise, if we don't have at least 3 students registering, I'm afraid the whole thing will be canceled. So we're basically out of time. Send me email and, also tell me how you'd like me to teach. I'm somewhat flexible. Although, as they say, you can't teach an old dog new tricks, and I'm certainly an old dog. All right, well, I'll say goodbye now. I think what I plan to do actually is to put this, I'm going to put this on YouTube as we did in the past. So that students who missed the first lecture could look at it. And of course, they can also read the book. What I'm saying is pretty much in the book. In fact, I was once told by John Ellis, the very distinguished theorist at CERN, that when he was taking quantum mechanics from Dirac, students complained that Dirac just read from his book. And students complained, well, why do you read from your book? We can all read your book. And Dirac said, well, I gave great thought to how best to explain quantum mechanics, and that's what I wrote in the book, and why should I do it differently and in class and explain things in a more confusing way? Anyway, that was Dirac's perfectly logical answer. Of course, I can't compare myself with Dirac. He was one of the greatest physicists of modern times, and has his footprints and fingerprints over most of theoretical physics. Anyway, all right, I'm going to stop the lecture now. So please find some people to take the course. Bye.